And like the quicker you get it, the quicker it'll increase your smart score and let you finish anyway. So it's good like that. Okay. Screen sharing. That also means it corrects it for me and I don't have to correct your work either, which helps. Okay, so the new concept today is limits, which basically, and again, I'm actually going to use IXL for this because it really focuses on graph, which is kind of a good way to see what limits mean. So, okay. So what a limit is if a function or if a set of numbers is getting closer and closer to some value, and it's fairly obvious that it's getting closer and closer to that value, that's what a limit is, okay? And we have a special notation for that. So say you're doing the example they give. Can you see my screen okay?
Yeah.
Yeah. So see this sequence of number, half, a quarter, an eighth, 1/16. So they're dividing by 2 each time, okay? So what we can see is as the numbers go along, they're getting smaller and smaller and smaller, okay? So that sequence of numbers is approaching 0. Would you agree?
Yeah.
Okay, so that's one thing to say. We could say the limit of each of the terms is 0. Okay, we didn't do sequences and series yet. A series is basically if you add the numbers. So a sequence is just a pattern of numbers, and a series is if you add those numbers. So if we were to add a half plus a quarter plus an eighth, obviously we're adding a smaller and smaller number each time, and by the time you get to the 10th term there, you're really only adding 0, so you're not making much difference to the sum. Does that make sense?
Mm.
Is that okay? That makes sense to people? What?
Yes.
Sorry, I just realized I left my phone on. I can hear my voice in the other room. Hang on a sec. Sorry, that's a bit weird. So the idea is a limit is basically a number that you get closer and closer to when you're looking at a pattern or a function, but you never actually reach that number. Okay, so well, sometimes you might reach it, but you can see that it's getting close to. Okay, so that's just a pattern of numbers. If we take a function, so something where we have an algebraic function, so basic 1x squared, and they've plotted the graph here. Okay, and we can see the f of 3 would be 9. Okay, we know that f of 3 is 9. Okay, what we want to do is say as we get closer and closer to 9, what can we say about the limit? Okay, and this is fairly obvious. Now, getting closer to, you could be approaching 3. Okay, on the x-axis, you could be moving from the left, so you could be starting at 2 and then going to 2.5, 2.75, 2.8, 2.9, and getting closer and closer to 3 from the left. Does that make sense? Okay, so what I'm saying is I'm moving along the graph from the left. My x value is getting closer and closer to 3. And what's happening to my y value? It's getting closer and closer to 9. Does that make sense?
Yeah.
So as I move along the graph from 2 to 3, my x is getting closer and closer to 3, and my y is getting closer and closer to 9. So what we say is the limit as x gets closer to 3 or tends to 3 is 9. The limit of y as x gets to 3 is 9. And then the same thing as if we were to start, say, at 4 and come down to 3 from the right. So as we're approaching it from the right-hand side, what's happening? It's getting closer and closer to 3. And you'll see when we go on IXL, you've sometimes got functions where they have a break in them, and the limit might be different when you're coming from the left and coming from the right, okay? So I just want the notation there, instead of saying the limit as x gets closer and closer to 3. We have a nice mathematical way of writing it. So instead of writing the full word limit, we just do LIM. And instead of writing x is getting closer and closer to a value, we just say x tends to, and we just use an arrow. So we do x arrow, and we write that under the limit, just so to make it all concise. Sorry, I'm trying to get my camera going. So what we actually say is, I'm looking at the line here, as x gets closer to 3, the value of x squared, or the value of y, or the value of f of x gets closer to 9. So 9 in that case is said to be the limit of f of x as x tends to 3. Tends to just means gets closer to. And the way we write that, we just write the first 3 letters lim. That's enough to tell us it's limit of x squared, which is our f of x. So it's the limit of the function. So in other words, what's happening to y as x gets closer to 3? And what's happening to y as x gets closer to 3 is it's getting closer to 9. So that's the limit. Okay. So we use the abbreviation LIM. And if you want to find the value of the limit, it's actually generally quite easy. You just have to sub in the value that x is getting closer to. So to find, it says in general, to find the limit of f of x, in other words, to find what's happening to y as x is getting closer to a, x tends to a, all you have to do is substitute in a instead of x in the function, where a is just a number. So a in the case we were just looking at would be 3. So if I want to, for example, the limit as x gets closer to 2, what's happening to this function 3x plus 2 over x plus 4? All I have to do is sub in the value 2 instead of x. Wherever I see an x, I'm going to put in a 2. So I've got 3 times 2 plus 2 over x becomes 2 plus 4. So everybody see what's happening there? I'm just subbing in the x value, which is written under the limit. It's 2, wherever I see an x. And that gives me the value of the function when x is equal to 2. And usually functions don't have a break in them, so you'll get a specific number there. Is that okay?
Yeah.
Sorry, I'm just fiddling around with my... So the main idea is what's happening to y as x gets closer and closer to some number. And that number we usually call a. Now, where you have problems is sometimes when you're dividing, we can't divide by 0. So see this function here, x squared minus 9 over x minus 3, as x tends to 3. Well, if x is equal to 3, then I'd be trying to divide by 0. And I'd also end up with 0 on top as well. And I can't figure out the limit there. Okay? That makes sense? Okay, so, and the reason I can't is because if you were to sub in x equals 3 in the function, you can't actually work out because you can't divide by 0. So you have to find some other method. And what that looks like on the graph is a little hole. Yes, okay, my camera's finally working. So I'll just show you. Actually, we could even, bear with me. I'm going to pull up graph on the computer. So, in that function. Algebra, whatever you want to call it. Algebra. Yeah. Right, if I want to put it in the function from that previous one, it is x squared minus 9 divided by x minus x squared minus 9 divided by The reason that's a straight line is because we can factorize the top and it ends up being x plus 3. But let's see if we do x squared. Now, see what's happening to that graph? There's a big gap. The graph is in 2 sections. Can you see that?
Yeah.
Everybody see the graph there? It starts, you know, going, as you're moving along, you're down in the bottom quadrant, you're getting bigger and bigger. Once you go positive, it starts to decrease. And then at x equal to 3, there's a big jump. Okay, we can't actually work out x equal to 3 is here. Okay. And that's where the graph jumps from the bottom half to the top half. So there's a gap in the graph. You see that?
Yeah.
Okay. So that's what we call a discontinuity. So that's why we can't work out the value in the graph. I'm going to just show graphs. Sometimes instead of a jump like that, you actually get a hole in the graph. So just to give you an idea here. You see those graphs, like you've got a straight line, you've got a little hole there. See that?
Yeah.
Okay. So in that case, and sometimes see this one here, you've got a jump there at A, so there's no limit at A. At B, as you're coming from the left, you're going to about 1. Okay, see the way as you come along the graph, you're getting closer and closer to B, you're getting closer and closer to 1. But if you were to start on the right and go backwards and get closer and closer to B, you're actually getting closer and closer to 1.5. So there's a jump in the graph. So the limit coming from the left is different to the limit coming from the right. Can everybody see that?
Yeah.
Is it big enough? And then in this case, if we're going to C, as we come along from the left, so approaching C from the left, our limit is about 2.5. See that? But approaching C from the right, my limit is actually 0. Okay, or close enough to 0. Do you see that? So there's 2 different limits there, and this green dot down here is the actual value of the graph at C. So the limit doesn't have to equal the value. So see the way at point B, the blue one is the included part, but the open one is not included. Everybody, do you know what I'm talking about there? You know the way when you're doing inequalities, you color in the bit that's greater than or equal to, and you leave open the bit that doesn't have the equals part. Remember that from inequalities?
Yeah.
Okay, so if we're coming along this function, this dot here, the colored in dot is part of the function. So the limit equals the value of the function. But if we're coming from the right, we have a limit, but it doesn't equal what the value of the function is because it's a jump in the function. So what this function, it's not continuous, it's jumping all over the place. Okay, so a continuous function won't have jumps like this. So our x squared that we looked at is continuous. As you move along the graph, there's no holes or gaps or jumps, okay? But if you have a discontinuous function, then you're going to have jumps, and then your limits kind of get messed up a bit, okay? So first way to find the limit is just sub in the value for x and see what you get. If you end up dividing by 0, then you could look at factorizing. So the most common method to look at limits, factorize the numerator and the denominator. And then you've got, so if you factorize the top, you've got x plus 3 times x minus 3, divided by x minus 3, and you're left with x plus 3. Everybody see what's going on there? That's the difference of 2 squares, x squared minus 9. Is that okay?
Yeah.
And then when we sub in 3, we get 3 plus 3 is equal to 6. If f of x, right, so if f of x is defined, so if this is our function x squared minus 9 over x minus 3, f of 3 does not exist because if we sub in 3 there, we'd be dividing by 0. but we can still work out the limit. So the limit as x tends to 3 does exist and it's 6, but we can't actually work out the value of the function itself at 6. I know this is a lot of kind of new concepts to take in, and that's where I think the IXL will be good, because you'll be looking at graphs and be looking at subbing in. So example 1 here, we're just looking at limits. So what this first part, limit as x tends to 0. So what's the limit of this function? What's happening to y as x is getting close to 0? So I just sub in 0 for x and I get 1 over 3. Is that okay? So it's very easy to work out the limits. In this next one, if I sub in, so we want the limit as x is getting closer to 2. So the limit of f of x, the limit of our function as x tends to 2, what's happening to the graph? If I sub in 2 there, I get 4 plus 2 minus 6 over 2 minus 2, I get 0 over 0. So I have a problem. So then I go back and see, well, can I factorize anything here and simplify this? And if you factorize the quadratic there, the x minus 2's cancel. And now if you sub in 2, you can work out that the limit is 5. Okay?
So it's basically just substitution.
Yeah. And if the substitution works out with the 0, then you go and see if you can factorize. Okay, so if you end up dividing by 0, you're going to factorize. So I'm going to, let's see.
Oh, okay.
And yeah, let's look. I'm going to skip the x tending to infinity. Well, we can do this. So the limit as x tends to infinity. So that means when you're going way out along the axis and x is getting really, really, really big. Okay. And also you can go to infinity in the positive direction or in the negative direction. Okay, so we could see from that first example, as x is getting really, really big, f of x, or 1 over x, is getting really, really small. Okay. So we're going to examine the limit of a function as the variable tends to infinity. And have you seen this symbol for infinity before? It's like an 8 on its side.
Yeah.
No. Yeah.
Yeah, it's just a sideways 8, and that's infinity, which means the biggest number you can possibly think of, and then some. Okay, so the limit as x tends to infinity of things. So now we can't, infinity is a concept, it's not a number, so we can't just sub it in like we were subbing in 0 and 2. So what you have to do is kind of use cop on, or just look and say, okay, let's pick some big numbers and see what's happening. So if I pick x equal to 10, that's 0.1. If I make it like much bigger, x equal to 1,000, that's 0.001. If x is 1,000,000, then it's 0.000001. So we can see that x is getting closer and closer to 0, or 1 over x is getting closer and closer to 0. Does that make sense?
Yeah.
So that's a very important limit there. The limit as x tends to infinity of 1 over x is 0. So anything over x is going to, or anything over some function of x is going to get closer and closer to 0 as x gets closer and closer to infinity, or gets bigger and bigger and bigger. Okay? And from that, the last line there, if 1 over x, if the limit of that is 0, then the limit of 1 over x squared is 0. And the limit of any number over any function of x is going to be 0, because as x gets bigger and bigger and bigger, the number on the top is going to get less and less important. Like if I had 5 over x, I would just have 0.5 here, 0.005, 0.000005, and it's still getting closer and closer to 0. So it doesn't matter how big this number k is. By the time you get to infinity, k is irrelevant. Does that make sense?
Yeah.
Okay. Now, to do the limits when x is tending to infinity, it's a little bit different because we can't sub in infinity. Okay. So what we do, and you're going to use this rule for every single one of these, if you're getting the limit as x tends to infinity, you want to end up with x being, the one thing we know is 1 over x is equal to 0, or anything over x or x squared is equal to 0. So what we do is we divide everything by the highest power of x that we can see in the whole expression. And then anything that's 1 over x or 1 over x squared or k over x is going to be equal to 0. So the first one there, if I have, I'm just going to write this out. Limit is x tends to infinity. So once you see infinity, you know, hang on, I can't sub that in. Okay, so when you see infinity, what you have to remember is that I'm going to divide everything by the highest power of x. So when I look through this, the highest power of x is x, okay? So I divide every single term by x. So 4x divided by x is 4. 1 divided by x is just 1 over x. 2x divided by x is 2. And 3 divided by x is 3 over x, okay? And that's an equivalent fraction because I've done the same to the top and the same to the bottom, okay? I've divided the whole, everything by the same thing, so I haven't changed the value of the fraction, okay? And now if I want to get the limit as x tends to infinity of this, I know that that's going to go to 0, and this is going to go to 0, so I'm just left with 4 over 2, which is equal to 2. Is that okay?
Yeah.
And then this one here, I'm going to divide everything by x squared. So that's going to be the limit as x tends to infinity of 3 minus 2 over x plus 4 over x squared over 5 plus 4 over x minus 3 over x squared. That's gone to 0, that's gone to 0, that's getting close to 0, that's getting close to 0, and I'm just left with 3 over 5.
Do you just like use the two first numbers, or is it just the
well,
net?
it depends. If they're equal, see the way they're both x squared, but if I had something like, basically if the power on the top is smaller than the one on the bottom, so say I had 3x minus 2 over 5x squared plus 4x minus 6, okay? So I have to divide everything by x squared now. That would give me 3 over x minus 2 over x squared, 5 plus 4 over x minus 6 over x squared. And that ends up being 0 and 0 and then 5. So it's 0 over 5, which is equal to 0. Okay? And the reason, if you think, if the one on the top has a lower power than the one on the bottom, then this one is going to get way, way bigger than the one on the top. So that's why the limit is going to end up being 0.
Would you not like factorize it?
No, you don't need to factorize because and you can't factorize that anyway. It's not going to factorize. No, once you see infinity, it's not about factorizing. It's just basically, if the two powers are the same, then yes, it's just going to be these two numbers. If the power on the top is smaller, then it's going to be 0. If the power on the top is bigger, so if I just swap those two, over 3x minus 2, then I'd be doing 5 plus 4 over x minus 6 over x squared, 3 over x minus 2 over x squared, and then I'd have 5 over 0. That means there's no limit. And the reason there's no limit is because this number is always, as x gets bigger and bigger, x squared is going to be way bigger than x. Because think about your graph of x squared goes like this. It goes up quite quickly. So as x gets bigger, x squared is going to be much bigger than x. So that is going to be much bigger than this. And when you're at infinity, that's infinitely bigger than this. So that's why there's no limit, because it's just going to go up and up and up and up and up. Okay, whereas this one, the bottom's going to be much, much bigger. So you're going to be dividing a number by a bigger number. So that's going to get, as this number gets bigger and bigger and bigger, you're going to get closer and closer to 0. But if they're both going up at the same pace, then you can just look at the 3 over 5. Okay, now the other thing I want to talk about is, I'm going to skip limits and slopes for now. And we're going to look at continuity. Okay, so this is page 207. And basically, continuous just means there's no gap. Okay, so if you look at this function, that's a cubic function, there's no gap in it, so I can say it's continuous. All right, so if you were drawing it, you wouldn't have to lift your pencil. And most of the functions that we do anything we've looked at so far is continuous, okay? But occasionally you can have discontinuous graphs, okay? So especially when x is in the denominator, because at some point that's going to equal 0 and we can't divide by 0. So there's a graph of 1 over x minus 1, x or 1 over x plus 1. X can't be equal to -1 because then we'd be dividing by 0. So you have this discontinuity at x. That should be -1 there. Okay, see where they've written discontinuity at x equal to -1. And there should be a plus in here. It should be 1 over x plus 1. Okay, so if you sub in values, if you sub in -2.5 and -2 and -1.5, you'll be able to get numbers for all of those. But if you sub in, like if you put that into your calculator and you put 1 over 1 plus -1 plus 1, you'll just get an error. So you can't work out the value here. We could get -1.01, we could get -1.02, but we can't work out -1. And then the same on the other side. So that does not have a limit, okay? And then if you look at this graph on the right, it's what's called a piecewise function, where the graph is in pieces. So there's one kind of formula for this part down on the left, and then there's a different formula for this part on the right. So it's called piecewise because it's in different pieces. Okay, so once you go past number 1 there, you're on a different function, okay? So in this case, the limit coming from the left is going to be different to the limit coming from the right, okay? So, and we have a new word here, just asymptote. Have we talked about asymptotes before at all?
No.
So an asymptote is a line that a graph gets close to but never actually crosses. So you can see this line here, x equal to -1. The graph gets closer and closer to that line, but it never actually touches or crosses it. It just jumps it. Okay, so it never touches it. And that usually happens when you have an x in the denominator. Okay, so an asymptote is just a line that a graph doesn't cross. Okay, that's all you have to know about asymptotes. So continuity, a function is continuous if the limit as x tends to a is equal to the function a. So basically, if we look at this function here, the limit as I come from the left is equal to 1, okay? So I can say, okay, that might be continuous, but the limit as I come from the right is equal to 2, which does not equal f of x. So f of 1 is equal to 1. See that? That's the black dot. If I sub in 1 into this function, I should get 1. When I do the limit coming along here, it's approaching 1. That's what's happening to the graph. But when I do it coming from this side, it's not getting close to 1, it's only heading towards 2. In fact, it's just stuck at 2. So there's a discontinuity there, and now the limit doesn't equal the actual value of the function. Okay, so in normal functions, continuous functions, when we sub in our x equal to whatever, we should get it just f of x. But if it's not continuous, then we won't. So here's an example here. Show that f of x is not continuous at x equal to 3. If I sub in 3 there, I get something divided by 0, which is not defined. I can't factorize that. I can't do anything, so I can't get the limit. So that means it's not continuous. Okay. So looking at exercise 7.2, we're just looking at the values of x where there is a discontinuity. So in number 1 here, what's the value of the discontinuity? X equal to what? Where is there discontinuity?
So 0?
Yeah, x equal to 0, there's a jump in the graph. What about here? They've even written it down for us. X equal to 3, there's a discontinuity. This one, x equal to -2, it's discontinuous. It just means there's a gap in the graph. This one here, discontinuity at x equal to 2. This one at x equal to -3. And this one, anybody recognize this graph? Anybody know what it's the graph of?
Oh, it's the. I
yeah.
don't know what you're talking about.
Tan.
It's tan x.
Hmm.
And remember, tan isn't defined for any multiple of 90 degrees. Okay, so that's minus pi over 2 plus pi over 2. There's a jump in the graph. And remember, it goes from, as you're going around the unit circle, it goes from plus to minus, plus to minus. Okay, so what I want to do is do some, I think the IXL stuff would be good for this as well. So I'm just going to go into that and assign you a couple of that. It's in 6 years skills again. Yeah, find limits using graphs. Yeah, okay, so we're just going to do simple ones where it's just looking at. So W1 and W3. So to determine if a limit exists, basically just looking, is there a gap? Now, it depends on the value. Okay, so see this one here. Does the limit as x tends to minus 9 exist? Oh, sorry. You basically look at the value for x and see, is there a jump at that value? Okay. So that's all we're doing. We're just going to be looking at graphs and seeing, are there limits? Okay. And then these are really easy. So okay. Skip that one. Okay, so that's in the 6-year things. It's W1, W3, and AA2. Okay, so you're not doing any calculations as yet. You're just looking at the graphs and understanding how limits relate to graphs, because that's important. Is that okay? And they shouldn't take too long. It's just looking at the graph and seeing, is there a jump at the value? Okay. So I'll stick that up on last one. Okay, is the So anyone, any questions? You okay on that?
No.
And everyone got their login details?
Yeah.
Okay. Right, I'll leave you to it then. Any questions, just send me a message. And I'll get back to you. Okay?
Thank you.
All right, lads. See you tomorrow.
Thanks.
Okay, take care.
Quem é o amor da vovó? Olha aqui pra cima que eu tô filmando, é pra mandar pra sua mãe o vídeo. Olha aqui pra cima, Kalane, Renata, Rebeca. Ei, ô Jorge! Meu Deus, olha aqui, Jorge! Acorda aqui, Jorge! Acorda!
Sorry, no foot fetish for you today. Try again tomorrow.